Welcome to the second day of neural networks for architects. We are on chapter 9, and this day is on the mathematical thinking which led towards neural networks. And in this chapter we want to talk about the combinatoric explosion. So let's have a look how it works. Combinatoric explosion is a principal problem we have as gravitational people with gravitational thinking, and there is a metaphor for that, how to most prominent. It's called the Laplacian daemon, and this simply says, from 1814, it simply says, if we know all the parts and the connections of things on this planet, we can't predict precisely what will happen. So the key problem is, and for that the demon is there, that we can't do it. And then Laplace, with probabilities, he introduced the conception of error and so on, as we discussed before. So, and if things get connected, it's this kind of curve they developed. The amount of things, of connections develop like this. There's a prominent example on exponential growth. It's this with the chess field, and then a king wants to pay 1 month 1 corn of rice, next month 2, then 4, then 8, 16, 34, 32, 64, 128, and so on and so on. And after, this is how to calculate these things, this evolvement of the growth of the numbers, and it is insane. Just to give you an idea, this is the amount of tons of rice on the square number 64. This is the world production of rice, and you meet the world production of rice already at the square number 30 in this contract. So there you see, boom, this is always about explosion and catastrophes. So we celebrate it as architects, for example, with these generative algorithms. This is a small recursive code, and here you see how it works. To create a tree, this is generation number 1, then it splits, then the splits split again, then the splits split again, and so on. And you see how it evolves. It gets more and more detailed, and these are the amount of lines needed to make this detail, and it's growing like this. So if you want to get the tree in all details, there's no end. So this is a rendered a tree, computer generated tree, and it makes a little more, but it simply can't grasp nature. So in this game of terms and terminologies, we say it's sensible if you can grasp more details, or it's beauty if it's in sync, and so on. But it never finds an end, and you affirm that there's not an end. So affirming that reality doesn't find an end is nature. So that we are part of it, of reality, and we never can find it fully. That's, I think, how the setup is for gravitational people. If we go to combinatorics, we see the same things. So, for example, if you have 4 different elements, white, light, gray, black, this is a code for that. In Mathematica it's called permutations. You can look it up, how all this is set up in combinatorics and how this is symbolized in this language. Interesting to go there. I told you Mathematica is a kind of encyclopedia, active, interactive encyclopedia of everything of the world, as Wolfram says. So therefore with combinatorics, this is an entry point to go there and look like in an encyclopedia what is around, to be able to talk of these things. So this is a code to make this combinatoric game here, and there, that's important now, it's 24 with 4 different colors. So I get back. If you go to 6 different elements and parts, then you already have 720 combinations. So you can imagine, again, it explodes. Very few parameters, very few parts, and bam. So therefore all systems are in trouble with this. All gravitational things are in trouble with this. So especially us, for example us, so you are almost finished. I not need to do add some additional details. Super dangerous, because there's always 4 times more work and details than in the rougher sketch. And again, 4 times and so on. You know that in principle. So this is what we know, how we fight that as gravitational workers. So what is interesting as well, you see this with the building information models. Building information models create an ontology or a taxonomy. So this is a scheme, or we call it a system or a structure of all the components of a building, how to describe logically and correct a building, any building. So and this ends up exactly with these problems. So if you want to have these things pragmatic and fast and error-free, you have to cut the amount of elements. So which means the architecture is always trivial. If you go to a reasonable architecture, this model always explodes. And you can't manage it in reasonable time with reasonable costs and so on. It's exactly this problem, which is interesting because this evolves and gets prominent. It's technology from 1970s, and it didn't change a lot. And it evolves and gets prominent today the moment the aliens don't need systems as we'd seen before. They don't have exponential growth. It's not their problem. We will see how they do in this chapter. So that's interesting. So, or here with computation time, just to give you an example that this gravitational problem is everywhere. So for example here, if you want to sort 1000 numbers, random numbers, sort them, this takes a certain amount of time. If you have 10 times more numbers, it's more than 10 times, you see it's 50 times more effort. And if you go again, it's a good algorithm, so if you go again 10 times more, it's, in this case, it's 20 times more effort. So it's a little tricky to measure that, but you get the idea. So therefore, it's always with software, you know that if you want to go professional, you need professional software. And there's not definitely, not explicitly more functions, it's not about that. It's if you can write a text or a letter with a software, it doesn't work for a book because combinatoric explosion. Good. This is a phenomena, it pops up everywhere, and we are fighting with that. So the prominent statement in mathematics is with Gödel, der Unvollständigkeitssatz, 1930. There's a lot of stories around this, 1979 with Hofstadter's Gödel, Escher, Bach. I grew up with that. So this simply says a system can't be, a logical system can't be complete and correct. So it's the same like Laplace, demon. So this means that every system all structures, all ontologies, all reasoning and so on needs bounds. You need pragmatic bounds and say, this is what I want to take for pragmatic reasons, and this is what I exclude. This is my environment. So I embed it in a natural environment, and I simply include the rest, include the parts of a machine, and they should run properly. So it's always like that, with all ontologies, all systems, all structures, all machines, and so on, and all functions, as we've seen. It is like that. So it's always a part of the world. It always excludes. So the other thing, a demon, this is what the aliens are doing, is the Maxwell demon. And the Maxwell demon simply decides, you can look it up, decides and doesn't touch anything. And by that, he's out of this problem, interestingly. And this is with the alien. So the Maxwell demon is an alien, and the Laplace demon is a kind of God figure knowing everything in gravity. So what we have with the aliens is, and we will show that in detail, how it works. Instead of having exponential growth, 1, 2, 4, 8, 16, as we'd seen in the examples, the imaginary of the aliens grows linear. It's only 1, 2, 3, 4, 5, or 2, 4, 6, 8, 10, and so on. It just grows linear. So, and the implications there are immense, because you don't stuck to the local, so you don't have to make a bounds. You don't think in bounds. You can picture the world and talk about it. This is what I always say with not understanding and so on, which is a kind of crazy and paradox, but we will see how it works and get more discussions about, arguments about this. For example, if you go with simulation, so then you simulate the behavior of particles, which are gravitational, they're particles, they're gravitational, and they are with exponential growth in what if you want to play with them, if you want to work with them, you have these combinatoric explosion. For example, if finite element systems, or if you want to have the wind flow and simulation there, you have all the parts, and then you have connections between these parts, and then you put some linear equations, Navier-Stokes equations to that, and so you say, okay, you push this, then it's pushing the neighbors, and it's blowing like wind or flowing like water. So, and the key problem is that one particle, for example, has 8 or what is it, 8 or 6 neighbors, and the neighbors have 6 by themselves, and so on. And then this is a combinatoric explosion. So if you want to be precise, you have to know all the neighbors of the neighbors of the neighbors, and which means boom. So therefore, with simulation, which is gravitational, you have to be pragmatic. You have to cut it. So you cut it in resolution, and you cut it in the area you're able to cover. So for example, it works pretty well if you simulate the airflow within a room or around some skyscrapers and so on. That works pretty well. But if you want to make it for a whole building with all the rooms, or if you want to hold for a whole city, boom, not working. Aliens do different. So we have 2 PhDs about that, and it's incredible. So aliens simply look there and they learn from simulations. They look at it and they put things equal, and then they simply say bum bum bum. They go and like tiling. So tiling is not exponential. It just makes it. They just tile and make it and done. And therefore I would say this is synthesis. So aliens synthesize things. Yeah. And this is linear. So therefore, with aliens, you can cover the whole city, you can cover all Switzerland, the whole world, easily. So you don't have to, if you want to have double area or double resolution, you don't need 4 computers, you just need 2 computers for the double. And therefore you're able to cover the world, even if they're getting connected like hell as we experience. This is why this is working. So they're aliens, these big companies. The backdrop of this is that it's always wrong. So as gravitational, you always try to do better, and you're working hard to do better in detail, to make the errors less. This is not the problem of the aliens. They're just sitting at the edge of the world at the end of the time. They're making pictures of the world, they're making it in difference, and they can make proper distinctions, and they can decide properly. But they know the moment they decide and do something, there will be errors. So because it's a decision, and they're not part of the game to do better, so not in the continuity, in the flow, they are at the border and they cut and make differences. Yeah, it's not about good and bad, it's about right and wrong. And it's always wrong. Therefore, they don't decide. So they were constitutions. So they're afraid of deciding, because they know it will be wrong. So here we have it. Here, for example, how this is done. It's not too. Yeah, it takes a lot of meditation. But it's not too alien, because we are doing it all the time. So look at this, for example. If we have this alphabet of, so if we are not working with numbers, gravitation people always work with numbers. So, and they hear the harmony of things. Aliens work with letters, with alphabets. Now we have 24, or doesn't matter, and we take 4 of them, and then we say T-R-E-E, and there's a tree. And it's beautiful. The tree is there in all details you can imagine. So, yeah, this is the alien way. They just talk. Yeah? And I would say the distinction between design, it's making, it's gravitational, and architecture, the crisis of architecture, if there's one today, is that they do design or do engineering. They should learn to talk with the aliens, or like the aliens, about the world. Architectures are always a miniature of the world. They should take a picture of the work and talk. And they should be generous about inviting all things, and you have to put that. So if you go with rendering, you want to, or if what we see with this parametric design, they want to control all details. And this is exponentially complicated. Look at this building there, Louis Vuitton in Paris, 4 terabytes of data and so on. It's insane. So just to control all things. You can do it better, but it's just super control with supercomputers. This exponential growth, and they're proud of it, that they use supercomputers. I think it's not about that. So as the word tree is generous to all trees in all their manners and kinds and styles and colors and genders they're welcome. So they show up, and it just depends on how good you can imagine these things. And you don't make any, you have no any prejudices, you don't make any decision, no specification. Tree invites all trees. This is the power of talking. And this is how aliens doing it. It's not specifying it and making it explicit. So therefore I think architecture should be, in contrast to design, optimization, parametering and so on, it should be generous and inviting all things that might come in all details, curious and without preconceptions. Yeah? So this I think is the alien turn we should look for. And this is in line with Vitruvius, with Alberti. Architecture constitutes and tempers open spaces. Design and engineering are specific. They stuck to a problem, they solve problem, they make it smooth, and they are running into the principal problem of all control, that it's getting exponentially expensive. So, now, next turn. If we said with the aliens, they are alien, and if we say aliens talk and we gravitational people work, or they're sensible, they do things. How to bridge it? How is it that they collaborate? So in mathematics, this is, it's always, mathematics is a royal path to learning because it's uncorrupted. So mathematics is not about, it's not about numbers or formulas or proofs, and it's not that. It's a most explicit, uncorrupted way towards how to think and what to think, because there's no pragmatics in that. So therefore, now I want to make a metaphor of numbers, how they work, to show you how is it possible that I can these crazy things, so that the working people needs exponential effort to do something, and that the aliens are able just to talk and make it with a linear effort. So of course the working people of gravity are offended by that. Or it's a story of the rabbit and the hedgehog. Just always there, it's faster, and you simply don't know why it is working like that. So all mobile phones and calling and so on, if you go 200 years back, people would say it's magic. It's all these stories about, now we call it bridging, how to get from reality to to the alien rationality. So this is an example to get an understanding of how this works. So this, for example, whether you know it from compound interest. So if you have €100, 10% interest rate, 12 years, this makes 314 euros. If you make it 100%, it's 400,000 euros. So if you make it 1 year with 100%, of course this makes 2 euros. Now, if you go with 100% but divide it by 365 and make it compound interest 365 on daily base, so then you don't get 2, but you get 2.7. That's interesting. So if you put that not on a daily base but on a millisecond base, on an infinite small base, then you have the Euler number. And it's this. So this is how to compute this crazy irrational number, how to compute it. This is to get it, there's a formula for that. This is how to get the formula running. And this is how to operate with the Euler number as a power. So what you now need is the Euler number, powers here is 12, and now this n with the 8 here simply says we want to have 8 digits. So, because if I put here e powers 12, then it stays like this, because with we are with the alien, so it's alien writing. So I don't with symbolic, so it's not with numbers. So we are not working with numbers in Mathematica. It's with symbols. So we are this alien writing, and not like here with gravitational. This is our curve. The inverse function is the logarithm. So if you go e power 12 and make the logarithm, so it's a logarithm on base e, I call it ln here, then you get back 12. This is the power series to make the algorithms doing that to a certain resolution. So what does it imply? What does it do? So this is if you don't have any abacus, any arithmetics and so on. If you want to add 6 plus 5, then you have to make 21 steps. It's an addition. So if you are in a gravitational primitive, gravitational setup, if you want to multiply 6 plus 15, then you have to take 90 pieces in place. So if you want to give a power as a primitive gravitational body, you need 470 billion steps. And this is out of reach. Exponential. So aliens from the edge of the world, they don't touch anything. So they have alien eyes. They look at it. And the alien look is implemented with the logarithm. So alien look at reality, for example 6, this is what they see. They look at 15, this is what they see. To make a multiplication, they simply add these two numbers. So this is how they talk about it, and then they give you per audio, they talk the result. And that's 90, the multiplication. So the same with the power. They look at the 6, they take the 15 out of this, they multiply these two numbers, and they talk it back to reality, which is the 470 billion. So, and you see, there are even no steps, but let's say this is 6 with, it's a multiplication of 6 and 5. These are 90 steps to make 470 billion steps. So they are kind of linear. And for gravitational people, that's magic. So what we have is the exponential and the logarithms are bridging. These are the senses of the aliens. They are bridging the two domains. The gravitational towards the light. Light is of no gravity. So in mathematics, it's called, in category theory, it's called bridges, it's called functors and inverse functors. And then the gravitational domain, it's called domain. And then we have the domain of light, it's the harmonic domain, and it's a geometric domain with the gravity. So if you want to have more of it, there's a theoretical mathematician, my friend Elias Zafiris, recently published book called Natural Communication. You find the link here if you want to see more about, if you want to trust my story. So having that aliens, or my hypothesis is This is adequate talking about our planet, making politics of our planet. It's not about working. So you're simply, so that is what they're doing. Huh? They come by, they don't touch anything, they make a picture of what you want to do, and they give you the result. They don't work. They talk. So, like landlords. And it's directly like that. A little snobby. So, therefore, if we go here with the Greens, most popular book for green movement, The Limit to Growth, that's the first cybernetic version of Malthus. Here, 1789. Yeah, he uses the exponential function, which came up with Euler, and uses it to make a fight. You should look it up. It's very interesting. Again, against Goldwyn, I think it's Goldwyn, the first French anarchist. And as a British, he fought this anarchism and he said this will not work. And this will be catastrophic because there's a limit of resources and so on. If you educate people, this will not work. It will be a catastrophe, and so on and so on and so on. So and it simply uses this Euler function to create crashes. And the Euler function always gets crashes if you don't use it as a bridge. Euler function is a bridge. This is alien voice. So if you take this voice for real, then you're out. And it always crashes because the aliens are super powerful. They simply don't fit to the planet. So, therefore it's a misuse for some reason. This limit to growth, you can look it up. It's the most prominent, it's with Meadow, the limit of growth in 1972. It's the first computer simulation of our planet. And it's using Malthus' algorithm to simulate the world. And it always crashes, of course. What else? So if we, and we will go with the next chapter, if we go with this Euler function as bridges, we don't lose, no, we take the alien stance about our planet, which means we somehow can talk adequately and making adequate politics about our planet. If we are afraid that everything gets too fast as workers and that all these machines kind of take over and so on, yeah, we always will lose. So, and with these stories we have there, we get blind for addressing what really is at stake, to find solutions for that. So, these are my stories for exponential growth, and this is this chapter. I hope you find it interesting, and see you in the next chapter on the law of large numbers and how to learn. Thanks for watching, and see you soon.